In the world of military aviation, the line between a student's first jet and a frontline combatant is getting dangerously thin. No aircraft blurs that line more than this, the Hongdu L-15 Falcon. Designed to train China's next generation of elite pilots, its creators made a critical decision to make it supersonic. That choice transformed it from a simple trainer into a potent, affordable light fighter that is now appearing in air forces across the globe, from Africa to the Middle East. This isn't just a story about a jet, it's about a calculated strategy to reshape the skies. The aircraft's story begins not in a sterile Chinese design bureau, but in the complex geopolitical and industrial tapestry of the post-Cold War world, a testament to a strategy of leveraging foreign expertise not merely for imitation, but as a foundation for surpassing the original concept. At the turn of the millennium, as the People's Liberation Army Air Force, PLA-F, began its monumental shift towards fourth-generation fighters like the indigenous Chengdu J-10 and the formidable family of Russian-derived flankers, the Su-27, Su-30, and their Chinese counterparts, the J-11 and J-16, it faced a looming crisis in pilot development. The existing training pipeline, reliant on older, less capable aircraft, was inadequate to prepare pilots for the complex, high-energy, fly-by-wire environment of these new machines. To bridge this chasm, China Aviation Industry Corporation the Stunt, Avionics, initiated a program for a new advanced trainer, and in a move characteristic of the era's pragmatism, contracted Russia's famed Yakovlev Design Bureau in 2000 to act as a technical and scientific consultant. Yakovlev was, at the time, deep into the development of its own groundbreaking trainer, the Yak-130, a subsonic machine that would later spawn the Italian Leonardo M346 Master. This consultancy provided the nascent L-15 program, led by chief designer Zhang Hong, with a proven and highly refined aerodynamic blueprint, saving invaluable time and resources in the initial design phase. However, to characterize the L-15 as a mere copy would be a profound misreading of Chinese strategic intent. While the visual similarities to its Russian-Italian cousins are undeniable, the tandem cockpit, the mid-mounted swept wings, and the prominent leading-edge root extensions, lurks, the Chinese design team, which Yakovlev's own Director General credited with the vast majority of the design work, made a pivotal decision that would fundamentally distinguish their aircraft. While the Yak-130 was conceived as a purely subsonic platform, Hongdu pursued a more ambitious and challenging path: supersonic flight. This was not a matter of prestige, but of doctrine. A subsonic trainer, no matter how agile, can only partially replicate the flight envelope of a supersonic frontline fighter. By engineering the L-15 for a top speed of Mach 1.4, Hongdu was creating a true lead-in fighter trainer, lift, capable of providing a much higher fidelity training experience, acclimatizing pilots to the unique challenges of transonic and supersonic maneuvering before they ever set foot in a multi-million-dollar frontline asset. This decision cascaded through the entire design, necessitating different structural considerations, more complex engine intakes, and, crucially, the integration of afterburning turbofan engines. The L-15 program was thus an exercise in strategic technology acquisition, using a foreign foundation as a springboard for a platform tailored specifically to the PLAAF's high-performance requirements. This ambition was not without internal challenge. The L-15 was developed in direct competition with the Guizhou JL-9, a less sophisticated and cheaper trainer derived from the venerable MiG-21 lineage. The JL-9 represented a lower-risk, entirely indigenous path, and the PLA's eventual decision to procure both aircraft suggests a doctrinal compromise, using the JL-9 for intermediate stages of training and the more advanced and expensive JL-10 for the final critical transition to high-performance fighters. After a mock-up was unveiled at the Zhuhai Air Show in 2004, the first L-15 prototype took to the skies on March 13, 2006, marking the beginning of a new chapter in Chinese military aviation. There is a certain dry humor in the fact that Russia, through Yakovlev, actively assisted in the creation of an aircraft that would later emerge as a direct and formidable competitor to the Yak-130 in the international arms market, a prime example of the often unforeseen consequences of short-term industrial collaboration. The physical form of the L-15 is a masterclass in modern aerodynamic design, meticulously crafted to serve as a kinetic simulator for China's most demanding fighters. Its architecture is dominated by a blended wing-body configuration paired with medium aspect ratio wings. But the most defining feature is the set of large, gracefully curved, leading-edge root extensions, or lurks, that flow from the cockpit area back to the wing roots. These are not stylistic affectations. They are the key to the aircraft's exceptional high angle of attack AOA performance. The Aerodynamics generates powerful, stable vortices that flow over the wings at high AOA, energizing the airflow and preventing it from separating, thereby maintaining lift and control far beyond the point where a conventional wing would stall. This design grants the L-15 the ability to achieve and sustain a maximum angle of attack of 30 degrees, a figure that is not arbitrary. It is a direct and deliberate replication of the flight characteristics of the flanker family of fighters, which are renowned for their super maneuverability and high AOA capabilities. For a student pilot, this means the L-15's airframe itself is a pedagogical tool. It physically teaches the muscle memory, sensory inputs, and instinctive reactions required to operate at the very edge of the aerodynamic envelope, effectively pre-calibrating the pilot for the frontline J-11 or Su-30. This drastically reduces the training shock and the number of costly flight hours required in the operational fighter, directly fulfilling the program's core objective of enhancing training efficiency while cutting costs. The airframe is stressed to withstand a G load of plus 8.5 G, further enabling it to perform the tight, high-energy maneuvers typical of modern air combat. The aircraft's dimensions are compact, with a length of approximately 12.4 meters, a wingspan of 9.4 meters, and a height of 4.7 meters. Its empty weight is a lithe 4,960 kilos, though its maximum takeoff weight has grown through its development from an initial 9,500 kilos to 11,600 kilos for the heavily equipped L-15B combat variant, reflecting its expanding mission set. The construction of this airframe reflects a modern approach to materials science. According to Ukrainian sources involved in the program, approximately 25% of the aircraft's structure is composed of composite materials. The use of carbon fiber reinforced plastics and other composites is critical for reducing overall weight, which enhances performance and fuel efficiency, while also offering superior corrosion resistance and fatigue life compared to traditional all-metal structures. The remainder of the airframe is constructed primarily from advanced aluminum alloys, likely including modern aluminum-lithium formulations that offer weight savings approaching those of composites, but with more predictable damage tolerance and lower manufacturing costs using established industrial processes. This balanced application of materials is engineered to give the L-15 a design service life of 10,000 flight hours, ensuring a long and cost-effective operational career for both domestic and export users. If the airframe is the L-15's body, its twin turbofan engines are its heart, and the story of its propulsion is a geopolitical saga in itself. The decision to use a twin-engine configuration was a fundamental one, offering significant advantages in reliability and survivability over a single-engine design. For an advanced trainer, engine redundancy provides an invaluable safety margin for student pilots. For a light combat aircraft, it means the ability to sustain damage and return to base, a critical consideration for missions over hostile territory or open water. This design choice, however, plunged the program into the complex world of international engine supply chains, creating a strategic dependency that would become both a catalyst for the aircraft's initial success and a significant long-term vulnerability. With no suitable domestic engine available at the time, Hongdu designed the L-15 around the Ukrainian Ivchenko Progress AI-222 family of low-bypass turbofans. The initial subsonic trainer variants, designated L-15A or L-15AW, were fitted with the non-afterburning AI-222-25 model. This engine, a two-spool design with a two-stage low-pressure and eight-stage high-pressure axial compressor, produces a static thrust of approximately 2,520 kilograms force, 24.7 kN. It proved to be a reliable and efficient power plant for the Advanced Jet Trainer AJT role. However, to achieve the program's supersonic ambitions for the lift variant, a more powerful afterburning engine was required. This came in the form of the AI-222K25F, where the F denotes forsage, the Russian term for afterburner. This engine, while sharing the same core, incorporates an afterburner section that increases its dry weight from 440 kilars to 560 kg but boosts its maximum thrust to a potent 4,200 kglf, 41.2 kN. It is this power plant that gives the L-15B its Mach 1.4 performance, transforming it from a sprightly trainer into a genuine pocket fighter. The engines are managed by a full-authority digital engine control (FADEC) system, which automates engine operation, optimizes performance, and reduces pilot workload. This reliance on a foreign supplier, however brilliant the engine, was always a strategic gamble. The geopolitical turmoil in Ukraine following 2014 placed the entire L-15 supply chain in jeopardy, turning what was once a pragmatic engineering decision into a pressing national security issue for Beijing. The situation created an urgent imperative to accelerate the development of an indigenous replacement, the Guizhou WS-17, codenamed Minshan. Developing high-performance jet engines is widely regarded as one of the most difficult technological challenges in aerospace, requiring mastery of advanced metallurgy, precision manufacturing, and the kind of tacit knowledge that can only be accumulated over decades. China's struggles in this domain have been well documented, with a long history of reliance on Russian engines for its frontline fighters. The WS-17 program thus represents a critical test of China's industrial maturity. Publicly available specifications for the WS-17 are scarce, but it is reportedly designed to produce between 4,700 and 4,900 kgf of thrust with afterburner, a significant improvement over its Ukrainian predecessor. The successful integration and mass production of the WS-17 will be a watershed moment, not just for the L-15 program, but for China's entire aerospace sector. It will finally sever the L-15's geopolitical tether, ensuring its production and export viability are no longer subject to the political climate in Eastern Europe and signaling a major leap forward in China's quest for true technological sovereignty. Until then, the L-15 remains a formidable aircraft whose ability to fly depends, rather amusingly, less on the engineers in Nanjing and more on the state of international relations with Kyiv. Moving from the physical and mechanical to the digital, the soul of the L-15 resides in its advanced avionics suite and flight control system. It is here that the aircraft truly distinguishes itself as a 21st century training platform, designed not just to teach pilots how to fly, but to immerse them in the complex, data-saturated environment of modern air combat. The cockpit is a fully glass environment, an architecture standard in all modern 4th and 5th generation fighters, eschewing the analog dials of older trainers for a suite of large multifunction displays, MFDs, in both the front student and rear instructor positions. The front cockpit is also equipped with a wide-angle head-up display, HUD, which projects critical flight and targeting information into the pilot's line of sight, allowing them to maintain situational awareness without looking down at their instruments. The entire system is managed through a hands-on throttle and stick, HOTAS control scheme, where critical functions for sensors, weapons, and flight controls are mapped to buttons and switches on the throttle and control column. By replicating this perfectly, the L-15 ensures that a student pilot develops the correct ergonomic habits and cognitive pathways from the very beginning of their advanced training. The true genius of the L-15, however, lies in its digital, three-axis, quadruple redundant, fly-by-wire, FBW, flight control system. In an FBW aircraft, there is no direct mechanical linkage between the pilot's controls and the flight surfaces. Instead, the pilot's inputs are sent to a bank of flight control computers, which interpret the pilot's intent and then command actuators to move the ailerons, elevators, and rudder in the most efficient and stable way possible. This system is what makes inherently unstable but highly agile aircraft, like the J-10, possible. In the L-15, this technology is leveraged for a revolutionary training purpose. The FBW system makes the L-15 a programmable aircraft. Its handling characteristics can be altered via software to mimic the feel and response of a wide range of other fighters. An instructor can load a profile that makes the L-15 feel as heavy and stable as a Su-30 on a bombing run, or as nimble and twitchy as a J-10 in a dogfight. This reconfigurability is an incredibly powerful and cost-effective training tool, allowing a single airframe to prepare pilots for multiple frontline types, a task that would have previously required several different specialized trainers. The L-15 is less a conventional airplane and more a flying simulator with live engines, capable of providing a tailored training syllabus in the real-world environment of flight. For the combat-oriented L-15B variant, this digital brain is connected to a sophisticated suite of sensors and electronic warfare systems. The nose is visibly lengthened and reprofiled compared to the trainer version to accommodate a passive electronically scanned array, PESA radar. This X-band radar can scan for both air and surface targets with a reported detection range varying in sources from a modest 75 kilometers to a more respectable 111 kilometers, a difference that highlights the critical importance of a decimal point in air combat intelligence. While not as advanced as an active electronically scanned array, AISA radar, the PESA represents a significant leap in capability for a trainer-class aircraft, enabling it to guide advanced munitions and conduct realistic beyond visual range combat simulations. The L-15B's defensive suite includes an integrated radar warning receiver, RWR, with antenna typically housed in a fairing atop the vertical stabilizer to alert the pilot to enemy radar locks, and an identification friend or foe, IFF, system to prevent fratricide. Furthermore, it can be equipped with dedicated electronic warfare pods on its underwing hardpoints, allowing it to act as a cut-price electronic attack or jamming platform, further blurring the lines between trainer and frontline combatant. The evolution from a sophisticated schoolhouse to a genuine strike fighter is most evident in the armament and combat capabilities of the L-15B variant. This version transforms the platform's potential into tangible lethality, equipping it with a versatile and surprisingly potent arsenal that allows it to perform a wide spectrum of missions, from air policing and counterinsurgency to credible air defense and precision strike. The key to this flexibility lies in its external stores carriage capacity. While the basic trainer versions feature 6 or 7 hardpoints, the L-15B expands this to a total of 9, 1 under the center line of the fuselage, 3 under each wing, and a launch rail at each wingtip. These pylons can carry a total payload of between 3,000 and 3,500 kilocalories of fuel, sensors, or ordnance. For air-to-air combat, the L-15B is equipped to handle a range of Chinese short-range, infrared homing missiles, such as the PL-5 Thuareg and the more modern PL-8. These are primarily for self-defense and within visual range engagements. However, the most strategically significant addition to its arsenal is the PL-12, also marketed for export as the SD-10A, an active radar-guided, beyond visual range, BVR, air-to-air missile. The integration of the PL-12, guided by the aircraft's PISA radar, is a game-changer. It elevates the L-15B from a simple light fighter into a platform capable of BVR combat, a domain previously reserved for much larger, more expensive fourth-generation fighters. This single capability has the potential to dramatically alter regional air power balances. It effectively democratizes BVR engagement, providing smaller air forces with a low-cost but credible deterrent against technologically superior adversaries. An Air Force equipped with L-15Bs can no longer be dismissed as having only a short-range defensive capability. It must be approached with the tactical respect due any BVR-capable opponent. In the air-to-ground role, the L-15B's capabilities are equally comprehensive. It can carry a centerline-mounted 23mm cannon pod for strafing runs, as well as unguided 57mm rocket pods and conventional freefall bombs. More importantly, it is fully integrated with a suite of modern precision-guided munitions. These include the LT-2 laser-guided bomb, which requires a targeting pod or a ground-based designator, and the highly effective LS-6 family of GPS INS-guided glide bombs. The LS-6, with its fold-out wings, can glide to targets up to 60 kilometers away, allowing the L-15B to strike defended targets while remaining outside the range of many short-range air defense systems. For anti-armor missions, it has been shown with the HJ-10 anti-tank guided missile, a formidable weapon capable of destroying modern main battle tanks. This diverse weapon set, ranging from BVR missiles to precision glide bombs, makes the L-15B a true multi-role combatant, capable of adapting to a fluid battlefield and providing its operators with a flexible and cost-effective solution for a wide array of combat scenarios. In the crowded global sky of advanced jet trainers, the Hongdu L-15 occupies a unique and strategically astute position. A comparative analysis against its primary international analogs reveals that it was not designed to be the absolute best in any single performance metric, but rather to offer the most compelling balance of modern capabilities at a disruptive price point. Its closest relatives are its subsonic cousins, the Russian Yak-130 and the Italian Leonardo M346, with whom it shares a common design ancestor. The Yak-130 is a rugged, reliable workhorse, optimized for operation from austere airfields with features like engine intake blanking doors to prevent foreign object damage. It boasts 9 hardpoints and a respectable 3,000 kg payload, making it a capable light attacker, but its performance is capped at a subsonic Mach 0.93. The Leonardo M346, particularly in its M346 Faye fighter attack variant, is a highly sophisticated platform with an exceptional embedded training system that can simulate a vast array of sensors and tactical scenarios, making it arguably the world's premier pure training and aggressor aircraft. It too, however, is fundamentally a subsonic design. The L-15's crucial advantage over both is its supersonic performance. Its ability to push to Mach 1.4 allows it to train pilots for the entire flight envelope of modern fighters and gives it a significant kinematic advantage in a potential combat role, enabling faster ingress, egress, and interception. The more critical comparison, however, is with the world's other leading supersonic trainer, the South Korean KAI T-50 Golden Eagle, and its FA-50 combat variant. The T-50 is a formidable competitor, a mature platform with a wider operator base and deep integration with Western systems. It is powered by a single, powerful General Electric F404 engine, a derivative of the engine used in the FA-18 Hornet, which gives it a slightly higher top speed of Mach 1.5 and a greater payload capacity. The FA-50 variant is equipped with proven Western avionics, such as the AN, APG-67, or EL M2032 radar, and can carry a full suite of American weaponry, including AEM-9 Sidewinder and AEM-120 AMRAAM missiles, making it an attractive option for nations aligned with the United States. Against this, the L-15 offers two key differentiators. The first is its twin-engine configuration, which provides a level of safety and redundancy that the single-engine T-50 cannot match, a powerful selling point for air forces concerned with pilot safety and mission reliability over water or remote terrain. The second, and perhaps most important, is cost. With a unit price estimated between $10 and $15 million, the L-15 is significantly cheaper than the F-A-50, which is often quoted at over $30 million per aircraft. This positions the L-15 as the quintessential good enough competitor. It may not have the absolute top-end performance of the F-A-50, but it offers a supersonic, BVR-capable, twin-engine platform for a fraction of the price. It occupies a strategic market niche, providing a modern feature set that is more advanced than its subsonic European counterparts, but far more accessible than its South Korean rival, making it a disruptive force for a vast segment of the global market that desires advanced capabilities without the exorbitant cost. The future of the L-15 platform is intrinsically linked to the grandest ambition of the People's Liberation Army: the creation of a world-class blue water navy centered on a fleet of modern aircraft carriers. The most significant development in the L-15 story is the recent emergence of a new prototype, spotted in flight testing in late 2025, featuring a radical redesign of its empennage. This new variant discards the single vertical stabilizer of the original design in favor of a twin-tail configuration with two smaller outward-canted vertical fins. This is not a minor aerodynamic tweak. It is clear and undeniable evidence of a carrier-capable variant in development. Every modification visible on this new prototype points towards the brutal operational environment of a carrier deck. The twin-tail design itself offers significant advantages for naval aviation. It improves directional stability and control during the critical high AOA, low-speed flight regime of a carrier approach, where precise handling is paramount. Furthermore, twin tails are shorter than a single tail of equivalent effectiveness, reducing the aircraft's overall height and making it easier to store in the cramped hangar bays below a carrier's flight deck. Accompanying the new tail is a visibly reinforced tricycle landing gear engineered to withstand the violent, controlled crashes of arrested landings, along with a new twin-wheel nose gear assembly to better distribute the immense forces of a catapult launch. While not yet seen, a housing for an arrestor hook is an almost certain feature of the design. This navalization program is not a speculative venture. It is a direct response to a critical capability gap. China's existing trainers, the land-based L-15 and the older JL-9, are not optimized for the rigors of carrier operations. As the plan commissions ever more sophisticated carriers, like the Type 003 Fujian with its advanced electromagnetic catapults, the need for a dedicated high-performance carrier trainer has become acute. An aircraft carrier is ultimately a floating airbase, and its combat power is entirely dependent on the skill of its pilots. Without an effective and safe training platform, the plan cannot generate the quantity and quality of naval aviators required to man its growing fleet of carrier-borne fighters like the J-15 and the next-generation J-35 stealth fighter. The navalized L-15 is therefore more than just a new variant of an existing aircraft. It is a critical enabling technology for China's entire carrier aviation enterprise. Its development serves as a bellwether of Beijing's naval ambitions. The successful entry of this twin-tailed Falcon into service will signal that China has solved a key piece of the enormously complex carrier aviation puzzle, and it will be a definitive statement of the seriousness and scale of its long-term maritime strategy. In the final analysis, the Hongdu L-15 Falcon must be recognized as one of the most significant Chinese military aircraft of its generation. Its importance stems not from any single revolutionary technology, but from what it represents as an integrated system and as a symbol of China's maturation as a global aerospace power. It is the physical embodiment of a sophisticated national strategy, showcasing an industrial doctrine that has evolved from simple reverse engineering to the shrewd acquisition and adaptation of foreign technology to create a product that surpasses its progenitors in key areas. The L-15's journey from a Yakovlev-influenced concept to a supersonic, multi-role combatant, and ultimately to a twin-tailed naval trainer destined for the decks of China's supercarriers, mirrors the trajectory of the nation's broader technological and military rise. It is a testament to a pragmatic design philosophy that skillfully balances the dual requirements of domestic force generation and international export appeal. For the Plafin plan, it is a vital tool for solving the pilot training bottleneck, a cost-effective flying simulator that prepares a new generation of aviators for the complexities of aircraft like the J-20. For the global arms market, it is a disruptive competitor, offering a package of speed, modern avionics, and advanced weapon capabilities at a price point that fundamentally challenges the established hierarchy of Western and Russian suppliers, as evidenced by its landmark sales to nations as diverse as Zambia and the United Arab Emirates. The aircraft's ongoing evolution, particularly the determined pursuit of engine self-sufficiency with the WS-17 and the development of a carrier-capable variant, underscores a methodical and relentless drive towards complete technological independence and full-spectrum military capability. The L-15 Falcon is, therefore, far more than just an advanced trainer. It is an aerodynamic system, a propulsion system, a digital training system, an industrial production system, and a geopolitical export system, all effectively integrated into a single, versatile airframe. Its enduring significance lies in this successful synthesis, which has forged the L-15 into a powerful and multifaceted instrument of national policy for the People's Republic of China.